Salutations! The video you have just seen is of a bowling ball being thrown out onto a bowling lane as depicted here. Before we can talk about the basic mechanics behind that, first we need to go over what a vector is, what it is versus a scalar, the components of a vector, and the vectors of position, velocity, and acceleration. A scalar is a quantity with a magnitude or value, such as 4. 4 is a scalar. A vector, however, is a quantity that has both a magnitude and a direction. Vectors are written as a letter or a group of letters that represent them, such as this vector, which starts out at P and goes to Q, is represented as PQ, and then an arrow is drawn above the letters to indicate that it is a vector. P is written first because it starts at P, goes to Q. The arrowhead on this vector is in the direction that it's pointing. The components of a vector is what the vector is doing in each dimension. The y and x dimensions in this case. In the x dimension, we have pq sub x, that is the notation used for vectors. That is equal to the value of pq multiplied by the cosine of this angle theta. In the y direction, pq sub y is equal to pq multiplied by the sine of this angle theta. We can get this through some trigonometry, and through the Pythagorean theorem, we can see that if you know the value of each component, you can figure out what the magnitude of the vector is, magnitude denoted by these absolute value bars, is the square root of the x component squared plus the y component squared. The three types of vectors we'll be talking about now are position, velocity, and acceleration. Velocity and position's relationship is that velocity is the change in position over time. That is, how position changes with respect to time. Those of you who've taken any calculus before know that that is the derivative. Acceleration, similarly, is the change in velocity over time. Again, the derivative. If we look at our bowler, for example, he threw the ball straight out in the positive x direction over the bowling lane. We can break up this two-dimensional problem into two one-dimensional problems in both the x and y directions, respectively. The position in the y direction, over time, is the ball comes off his hand and falls to the lane. In the x direction, the position is constantly increasing. The velocity in the y direction, since he started out throwing the ball solely in the x direction, the velocity in the y direction starts out at 0 and constantly decreases. X keeps a constant velocity, which just happens to be that same value v0, because the initial velocity was only in the x direction. The acceleration is how the velocity changes over time. In the x direction, the velocity is not changing at all, so the acceleration is constantly 0. In the y direction, the velocity is constantly decreasing, so the acceleration is a constant negative value. The reason that the ball is going toward the lane is the acceleration due to gravity. Since we are on planet Earth, I hope. Now let's look at a different path. Had the ball been thrown along this green path, upward into the air first, it would be modeled as such. We can draw the velocity and acceleration right onto this position graph. Initially, there is a velocity, v0, in both the positive x and y directions. As the ball travels, acceleration due to gravity is pulling the ball down toward the surface of the Earth. No, it's still in the bowler's hand there, so I won't include that. As this is happening, the velocity is likewise changing. To write a vector, you can put its x component, comma, its y component inside of bent brackets, or you can say x I hat plus y j hat. The hats simply indicate that it's the vector the same way the arrow above the letter does. The difference between 2D and 3D motion is that you have a third component in 3D motion, x, y, and z, which if you're using the I plus j notation, now you have a k with a hat. You can still break this down into multiple one-dimensional problems to make them easier to solve. With 2D, we break it down into two 1D problems. With 3D, we just break it down into three 1D problems.